In the earlier lectures on alcohol, we have discussed monohydric alcohol in detail. We have discussed various classes of monohydric alcohols, their properties and various reactions which they undergo. Now, in the present lecture, we will discuss mainly dihydric alcohols. Dihydric alcohol, as the name implies, are the alcohols which contain two hydroxy group in one molecule. Well, dihydric alcohols are the alcohols which contain two hydroxy groups, and they are classified as alpha glycols or beta glycols depending upon the relative position of hydroxy groups. If the two hydroxy groups are present on adjacent carbon, they are called alpha glycols or 1,2 glycols, whereas beta glycols are the alcohols where the two hydroxy groups are present on relative 1 and 3 position. 1,1 glycols are the molecules or are the dihydric alcohols which have two hydroxy group on the same carbon. This kind of molecules are quite unstable, but the only exception to 1,1 glycols which are quite stable are the acetal and ketals of aldehyde and ketones. Aldehyde, when react with alcohol, they form acetal, which are 1,1 diols. We will now discuss the nomenclature of dihydric alcohols. The common names given to the dihydric alcohols are on the basis of alkenes from which they have been derived. For example, 1,2 glycols, if they are derived from ethene, they are called ethylene glycol. If 1,2 glycol derived from propylene, the final molecule is propylene glycol, but this is the common name given to alpha glycols. In IUPAC nomenclature, the class suffix for 1,2 glycols is diol, and the number of hydroxy group present in the main chain is given according to their position, as well as the substituents present therein also. The rule of largest possible carbon chain is also implies here in the nomenclature of diols. Here you can see in this example, this main chain contains 8 carbon atoms and the terminal carbons have the hydroxy group. So, basically this molecule is octane 1,8 diol. If we number it from here, we see that the position of methyl group come at position 4 and position 6, whereas if we number it from here, the position comes out to be 3 and 5. So, you can very easily decide that the right name, right IUPAC nomenclature for this molecule will be 3,5 dimethyl octane 1,8 diol and not 4,6 dimethyl octane 1,8 diol. In the next case, you can see that the hydroxy groups are present on position 2 and 4, whether we number it from here or we number it from here, position 2 and 4 have the hydroxy group. So, the molecule is 2,4 diol and position 2 and 4 has a methyl group also, that is why finally the name given to the molecule is 2,4 dimethyl pentane 2,4 diol. In this example, you can see that the terminal carbon has a hydroxy group, whereas fourth carbon again has a hydroxy group. Position 2 and 4 have a phenyl substitution. That is why the name given to this molecule is 2-methyl 2,4 diphenyl pentane 1,4 diol. And in the next example, the name given is 2,3 dimethyl butane 2,3 diol. This molecule is also called pinacol. We will now discuss the physical properties of dihydric alcohols. Diols have two hydroxy groups through which they can have intermolecular hydrogen bonding. Thus, they exhibit much stronger association, and this can be seen in the form of their higher boiling point and higher solubility in water. Propane 1,2 diol has a boiling point of 186 degrees, whereas propane 1,3 diol has a boiling point of 214 degrees. If we compare the boiling point of these diols with that of alkanes or alkanols, we find that they are much higher, and the reason behind the higher boiling point of diols is their possibility or their nature of association more than monohydric alcohols. Dihydric alcohols also show high solubility in water and they have high viscosity also. We will now discuss the preparation of dihydric alcohols, and in particular we are going to discuss the preparation of ethane 1,2-diol or ethylene glycol. Ethylene glycol is the simplest dihydric alcohol and can be prepared by the oxidation of ethene. Ethene, you know, can be prepared by the cracking of petroleum. Now, ethene when undergoes reaction with alkaline dilute potassium permanganate solution or with osmium tetraoxide, it forms ethylene glycol. Here the formation of ethylene glycol via this method is a cis addition, that is only on one side of the double bond addition of the two hydroxy groups takes place. Ethylene glycol can also be prepared by the epoxidation of ethene. Epoxidation is a method in which ethene is reacted upon with oxygen in presence of silver catalyst under pressure. Ethylene, first there is formation of epoxide and then the epoxide hydrolyzes to ethylene glycol. This method is used in for the industrial preparation of ethylene glycol. Ethylene glycol can be prepared by the formation of chlorohydrin from ethene followed by hydrolysis. In this case, ethene is treated with hypohalous acid, which in turn is prepared by the reaction of chlorine with water. This hypohalous acid adds on to the double bond of the ethene molecule, forms ethylene chlorohydrin, which upon hydrolysis forms ethylene glycol. Ethylene glycol can be prepared from vicinal dihalides. Vicinal dihalides are the molecules where two halogen atoms are present on adjacent carbon atoms. Like for example, ethylene dibromide when treated upon with aqueous sodium carbonate solution produces ethylene glycol. The yield of ethylene glycol here is quite low because this reaction, a byproduct vinyl bromide is also formed and that reduces the yield of ethylene glycol. If instead of aqueous sodium carbonate, sodium hydroxide or potassium hydroxide is used in the same reaction, then it has been seen that instead of formation of ethylene glycol, vinyl bromide is the major product, and the reason behind it is that this sodium hydroxide and potassium hydroxide are quite strong bases as compared to sodium carbonate and they undergo elimination rather than substitution. The best yield of glycol is obtained by heating vicinal dibromide with potassium acetate in glacial acetic acid. The diacetate formed upon hydrolysis forms ethylene glycol in good yield. Ethylene glycol can also be prepared by the reduction of glyoxal like glycolic aldehyde like oxalic ester. All these molecules when reduced with sodium in ethanol, they form ethylene glycol. Another method of preparation of ethylene glycol is from ethane 1,2-diamine. Primary amines we already know upon reaction with nitrous acid forms alcohol. Here we are using diamine, so diamine is converted into diol. 1,2-ethylene diamine when treated upon with sodium nitrite in hydrochloric acid forms ethylene glycol. We will now discuss the reactions of dihydric alcohols. Dihydric alcohols, as we know, contain two primary hydroxy groups. So, they will undergo the reaction which normally are given by primary hydroxy group, but since we have here two hydroxy group, the reaction will be a bit different from what we have earlier done in case of primary alcoholic group. Let us see what happens here when ethylene glycol is treated with sodium metal. You can see here that at 50 degrees when the reaction is done with ethylene glycol, monosodium salt is formed, but if we keep on heating the solution to 160 degrees, disodium salt is formed. Or in other words, we can say that replacement of one hydroxy group by sodium metal is easier, but the replacement of second hydroxy group by sodium metal is difficult. The reason behind it is actually the presence of this alkoxy group. This alkoxy group increases the electron density on the adjacent carbon, thereby makes the carbon oxygen bond stronger and the removal of this hydroxy group difficult. When ethylene glycol reacts with hydrochloric acid or hydrogen chloride, then we see again the same trend, that is at about 160 degrees centigrade only one of the hydroxy group is replaced, but if we keep on heating to 200 degrees centigrade, then we see that both the hydroxy group are replaced and we get ethylene dichloride. Now, in this reaction actually is an example of nucleophilic substitution reaction in which chlorine is replacing hydroxide. Once a hydroxy group is replaced, chlorine because of its minus I effect takes away the electron density between this carbon and oxygen towards itself. As a result, this carbon oxygen bond gets stronger and formation of oxonium ion here becomes difficult, and that is why we require drastic conditions for the conversion of the second hydroxy group into chloride. Ethylene chlorohydrin, which we prepared by the simple reaction of ethylene glycol with hydrochloric acid, can also be converted into beta hydroxy propanoic acid, in which case what we do is we treat ethylene chlorohydrin with sodium cyanide, chloride is replaced by cyanide, and then this molecule upon hydrolysis forms beta hydroxy propanoic acid. Here actually if you look at this molecule, it has 2 carbon atoms, and here we have prepared a molecule which has 3 carbon atoms. So, this is a very good synthetic method for the conversion of 2 carbon alcohols into 3 carbon hydroxy acids. Ethylene glycol reacts with phosphorus trichloride and phosphorus tribromide to form corresponding ethylene dichloride and ethylene dibromide. Here ethylene glycol is reacting with PbR3 to form ethylene dibromide. When the reaction of ethylene glycol takes place with phosphorus triiodide, diiodide is formed, but this diiodide is quite unstable and ethene is the final product which is formed upon iodination. Ethylene glycol, when treated with concentrated nitric acid, it forms ethylene dinitrate. This ethylene dinitrate is also called glycol nitrate, and this glycol nitrate is used as explosives. Ethylene glycol, when reacts with acetic acid or ethanoyl chloride or acetic anhydride, it forms glycol diacetate or ethylene diacetate. With dicarboxylic acid, condensation polymers are formed, whereas with monocarboxylic acid, diacetates are formed. We will discuss here in this slide the preparation of condensation polymers of ethylene glycol when they are formed by the reaction of dicarboxylic acid. Ethylene glycol reacts with terphthalic acid to form polyester, which trade name of which is terylene or Dacron. This is ethylene glycol. This reacts with terphthalic acid, benzene 1,4-dicarboxylic acid to form this condensation polymer. Ethylene glycol can also form condensation polymer with aliphatic dicarboxylic acids. Ethylene glycol reacts with aldehyde and ketone and forms cyclic acetal and cyclic ketals. This cyclic acetal and cyclic ketals, which are formed after this reaction, are used for the protection of aldehydic group. Now, some dehydration reactions of ethylene glycol. Under different conditions, ethylene glycol give different product of dehydration. For example, when ethylene glycol is heated at 500 degrees, it forms ethylene oxide. When heated at heated with anhydrous zinc chloride, the product is ethanol, whereas when distilled with fuming sulfuric acid, dioxane is produced. Dioxane is a good solvent. Now, some oxidation reactions of ethylene glycol. Oxidation of ethylene glycol gives a number of oxidation products like glycolaldehyde, glyoxal, glycolic acid, glyoxalic acid and oxalic acid. Out of these oxidizing agent, glycolaldehyde, glyoxal and glyoxalic acid are quite unstable and are obtained in poor yield. The reason behind the poor yield of these oxidized product is that they are quite unstable and they are transformed into more stable glycolic acid and oxalic acid. Now, we will discuss oxidative cleavage of dihydric alcohols. When the carbon-carbon bond between the two hydroxy group containing dihydric alcohol is broken because of oxidation, the process is called oxidative cleavage. This oxidative cleavage can be possible with the help of lead tetraacetate or periodic acid or sodium bismuthate. Here ethylene glycol when treated with lead tetraacetate forms two molecules of methanol or formaldehyde, and propane 1,2-diol when treated with lead tetraacetate or periodic acid forms one molecule of ethanol and one molecule of methanol. Cyclic diols on the other hand forms only one aldehyde and the number of carbon atom remains the same. Here this is cis 1,2 cyclohexane diol. This diol when treated with periodic acid, it forms hexane diol. The bond breaks between these two carbon atoms and a diol is the final product. The mechanism of periodic acid oxidation of glycol is divided into two steps. In the first step, there is formation of a cyclic periodate. Periodic acid reacts with the glycol and forms a cyclic periodate, and in the second step, redistribution of the electrons within the 5-membered ring takes place, which results in the breaking of this carbon-carbon bond and formation of two aldehydic groups here or two aldehydic compounds here. Diols undergo oxidative cleavage in presence of acidic or alkaline or neutral potassium permanganate, even in presence of acidic dichromate or chromic acid, two carboxylic acids. The product formed contains less number of carbons than the starting diol. Like for example, ethylene glycol forms two molecules of formic acid or methanoic acid. Propane 1,2 glycol forms one molecule of ethanoic acid and one molecule of methanoic acid by the oxidative cleavage of the molecules in presence of potassium permanganate. So, in the present day's lecture, we have so far discussed various classes of dihydric alcohols, what actually are dihydric alcohols, their nomenclature, some of their physical properties like their solubility, like their hydrogen bonding or their dielectric constant. Then we have discussed the reactions shown by glycols. In reactions, we have done the reaction of glycol with PCl3, with PCl5, with PI3. We have also done the dehydration of glycols. We have also discussed the condensation polymerization of glycols, oxidation and oxidative cleavage of ethylene glycol. And in the next lecture, actually we will first discuss the pinacol-pinacolone rearrangement. Pinacol-pinacolone rearrangement is a very important named reaction and it actually involves 1,2 diols. In this present lecture also, we have mentioned pinacol in the slide of nomenclature. We will also discuss trihydric alcohols in the next lecture. Thank you very much.